Hello everyone. Today we will talk about gas dehydration. Gas dehydration is one of the most important processes in oil and gas industry all over the world. In general, gas is coming from wells saturated with water. However, this water causes a lot of challenges to oil and gas industry, including corrosion, hydrate formation, and also decreases the heating value of the gas, and so on. So we have to get rid of this water. In the case we have today, we need the water dew point to be negative 10 degrees Celsius at 6200 kilopascal. We will learn how to do that in reality by simulating a dehydration system using triethylene glycol to absorb the water. First, have a look on the gas dehydration document to see the drawing of the system. It consists of a column where absorption takes place between triethylene glycol and water. Then the rich stream goes to the regeneration system in another column by reversing the operating conditions to be low pressure and high temperature. First, let's add a stream. Let's add the composition, So the composition we have from the document: nitrogen, hydrogen sulfide, carbon dioxide, C1, C2, C3, iso C4, normal C4, iso C5, normal C5, water, and a triethylene glycol. The fluid package, we will select pink Robinson and then go to the simulation. The first thing we will do to define a gas stream. I called feed gas. The composition we have here, it's on molar fraction basis, and as we learned before, make sure that the summation is 1. If it's not 1, this means that you have entered something wrong. And if the composition you have, the summation of it is not 1, we have to normalize it, and I'll tell you how. So now the summation is 1, it's okay. If the summation is not 1, and we are sure that we have entered the composition correctly, it's 99% for example, we can press on normalize, and HYSYS will distribute the difference among all these components. Then, okay, go back to conditions to record the temperature, 30 degrees Celsius, the pressure, and the flow rate. Now the stream is defined. I will add another stream by F11, which is triethylene glycol feed. So the temperature 50 degrees Celsius, the pressure and standard flow rate, and the composition we have, but remember that the composition we have is a mass fraction, not a mole fraction. So it's 1% H2O and 99% triethylene glycol. Now it's okay, the stream is defined as well. However, the feed gas we have, I have to change this name, triethylene glycol feed. Yeah, here you go. The feed gas we have does not have water. It's free of water because it's analyzed after removing water. However, we want to simulate the water saturated gas. To add water to it, we have to create a water stream. I call it free water, and the composition is 100% water. Now go to conditions. The temperature according to the case we have, 30 degrees Celsius, and the flow 0.5 kilogram mole per hour, and the composition is water as we said. However, we do not have a pressure, as you know. But now we can mix both together. So open the mixer, the inlet streams, feed gas, and free water, and the outlet will be gas plus H2O. Now this stream is not solved because it does not have a pressure, but we will ask the mixer to equalize pressures, so now they are both solved. Then we can add a separator just to remove the excess water and to make sure that the gas is saturated. The inlet is gas plus H2O, and the vapor here we have saturated gas and the liquid free water too. Now it's solved. However, as we said, make sure you have free water outlet of the liquid phase. Here you go, we have a mass flow. It's not zero, because if there is no water liquid here, this means that the gas is not saturated and it absorbed all the water and it did not reach saturation. In this case, you need to add more water here to saturate the gas. Now we have saturated gas. However, don't be angry with me. There is a more simple way to saturate gas without all this hassle. Just copy this stream, feed gas, and also copy free water stream. Here you go. And add something here called stream saturator. This one, stream saturator. Add both, feed gas 2 and free water -2. And the product name, we will call it gas plus H2O 2. However, it's not solid because we do not have a pressure. Just remove the molar flow from the water. We will let the saturation tool to do it itself, and we will add the gas, the pressure here, the same pressure for the feed, which is 6200. Now it's solved. This is another way to saturate the gas, and let HYSYS calculate the amount of water required to saturate this gas. Now this stream is equivalent to this stream. You have the two options. Now you know the two options. I'll delete this. There's no need for it. And now we have a saturated gas. Now let's add a simple absorber. From here, I'll add an absorber. Just double click on it. 8 stages. Triethylene glycol is coming from the top, and gas is coming from the bottom, saturated gas. And the overhead outlet is dry gas, and the bottom outlet is rich triethylene glycol, because this triethylene glycol is rich with water. The top stage pressure and the bottom stage pressure according to the case we have. Now we can run the column. Let's first check the degree of freedom. Degree of freedom is 0, no specifications required. Now run the column, it's ready conversion. Let's check water before and after. This is saturated gas with water. The composition of water here is 0.09%. What about after? 0.01%. So the water decreased dramatically in the gas. But wait, it's not that easy, because the main challenge with the absorption columns is the regeneration cycle, either for dehydration, sweetening, or carbon dioxide removal. we need to remove the water from triethylene glycol, from this rich triethylene glycol, to be reused again here. And this is not an easy process. As we said before, we will reverse the operating conditions, so do not forget, we will decrease the pressure and increase the temperature. First, please save your case. I call it dehydration. Now we will add a valve just to decrease the pressure of the rich triethylene glycol, and the outlet is low pressure triethylene glycol. However, it's not solved because we don't know what the outlet pressure is. Now let's add a heat exchanger. So shell inlet is LP triethylene glycol, which is coming from the valve, and shell outlet is region feed. This stream will exchange heat with the lean triethylene glycol coming out from the region process, the regeneration process that we will simulate. So the tube inlet is region bottom, which is the triethylene glycol coming from the regeneration column bottom, and the outlet is lean from lean to reach heat exchanger. Then go to parameters, simple endpoint. For delta P, we have it here at 70 kilopascal for shell, and the same for tube. Deactivate using the FT, and now the region feed temperature, which is this stream, should be 105 Celsius. So we'll go to worksheet, region feed, we will record the temperature 105 Celsius and the pressure to be 110 kilopascal. Now you can find that the LP, low pressure triethylene glycol, and region feed streams are solved, but the region bottoms and lean from lean rich heat exchanger are not, because we know nothing about them. Now it's time to add the region column.